Good morning, everybody. Thanks for this opportunity. So I'm Claudia Fabiani, researcher at Perugia University, as Tony and Marco was saying, I will be presenting in a few slides our experience with the Italian pilot of Santa Pollinare in Perugia. So Perugia is in the very center of Italy, and let me switch. Okay, and the main thing, let's say, about our demo site is that, as Tony was saying, it is actually an historic building. The building is a fortress, to be honest. So it's actually something very important in terms of art and history. And we are very much focused in art and history here in Italy. So you should be very careful when you try and touch this kind of buildings. It is a medieval fortress, which is right between Perugia and the Trasimeno lake in the countryside of the Umbria region here in Italy. And as you may understand, it is in the center of Italy, the very heart of Italy. And even though generally Italy has a quite temperate climate, in our case, we are in some kind of humid situation. So the climate is more or less humid, subtropical here. And this is the only region in Italy, in central Italy at least, that doesn't have any touch with the sea. So it's not in close contact with the sea. So we are in a sort of continental situation, even though it's fairly different from the continental of Central Europe. So the main thing about the Santa Pollinare fortress, as I said, is that it is something that has been there for centuries. It's been there for centuries, and it's composed of 3 different buildings, 3 detached buildings. The main fortress, which is the thing that you can see here. Then we have the dry and clean, that's something down here. And then the main pilot building, which is the former stable that served the fortress and is the thing that you can actually see here. Another quite interesting thing of our demo site is the fact that it has already went through a sort of retrofit and renovation in the 200s. That led this building to be the first building in the world to be to get a certification, which is the Green Building Council certification for historic buildings. So the GBCHB certification. And to be honest, this was like the pilot building for this kind of certification itself. So it was quite an important, pilot to choose, to be chosen. As I said, this dates back to the 200s, and essentially the building already went through the renovation in terms of building envelope, in terms of using recycled materials, high albedo materials, and of course went through seismic renovation and energy efficiency renovation. So the building already had a paving system for heating and a mechanical ventilation within it. So when we decided to actually consider and select this building as a pilot of the GEOFIT, we were really playing our odds, let's say. So in general, when you go through and you want to use geothermal applications for the additional energy retrofit of a building, you need to go through quite a huge design phase. And this, of course, was the case of our building. I don't know why I can't go on. Okay. So as you see here, that generally what you should do, what is nice for you to do, is to go through a specific retrofit procedure. First of all, you need to define some performance, some criteria that you want to go through during the renovation process. Then you need to develop strategies for these actions. And then you need to go through with a huge number of simulations. I don't know why. I don't have the control anymore. Can you hear me?
Yes, we do.
I
So
just
what's the
saw you
matter?
also. I think you must have the control.
Was a link included in your presentation, Claudia?
What?
Was a link to an external website, for example, included in your PowerPoint?
No, nothing.
Nothing? And now?
Okay.
I think that you must have it.
No, I'm not actually.
Okay, I will do it again. No, it's you are the. I will take it off and put it here again. So now, can you try?
No. Oh,
yeah.
Wait.
Yeah, it works.
Okay, now it does work.
Yeah.
Okay, good. So sorry about that. As I was saying, you need to go through lots of simulations, and then you need to evaluate your results, and then you need to take design decisions based on your results. So if you get good decisions, you go on. If you don't, you go back to the first step, and you need to optimize your designing procedure, your energy retrofit procedure. Once you complete that, and you get the efficient result that you were expecting, you can actually go through with your plan, and you can actually implement your strategies. So in our case, as Marco was saying before, we wanted to design the system mainly considering three main elements. So the ground heat exchangers, the hybrid heat pump, and of course the interface between the new and the existing system. As I said, we already had a paving system for heating, not for cooling though, and we already went through an energy retrofit of the building. So we had already a BMS, a building management system, that was actually controlling the system. So we need to somehow add something to work with what was already there, and we had to do it considering the main characteristics of the building, which is by itself a peculiar case because it's a historic building that really makes use of large thermal inertia in order to guarantee thermal comfort condition within its the inside, let's say. So in terms of ground heat exchangers, we used closed loop GHEX for producing both heating and cooling. And of course, we had to design and to decide where to implement those. As you can see here in the plan, the building, the one that we were actually focusing in, the former stable, is the L-shaped element on the bottom left of the slide. And we decided to place the heat exchangers on the green area that you see on the right. That is a free area that is actually at service of the fortress. So we were assuming that it could be a nice solution. Of course, in order to decide the main characteristics of the ground heat exchangers, we went through some kind of simulations, as I told you, assuming and defining the heating and cooling thermal loads for our building, and then actually designing the characteristics of the ground heat exchanger itself. We designed, of course, also the kind of excavation and then kind of backfilling that we were assuming to use, and then we went through with the designing of the overall GHEX, which in our case was a special kind, was a slinky ground heat exchanger, which means that it is a kind of superficial heat exchanger that is actually producing coils, as you see here in the slides. Okay, it's something that actually develops on a planar surface rather than go through the thickness of the ground, and really was like useful in our case because as we were analyzing and checking with radar and so on, the ground in our case was quite rocky bad, so we couldn't go too much in deep in the ground, and this was the best solution in our case. So the design went through the calculations, and the design team went through the calculation, and we decided to use 5 tranches of this slinky GHEX with a main distance of 1.35 meters between each of them, and then a ring diameter of 1.5 meter to be used. The second element that we had to design, as I said, was the hybrid heat pump. The heat pump that in our case was, as I said, hybrid, which meant that it was actually using gas boiler to start the production of heat. Our heat pump is actually composed of three elements. As I said, the gas boiler, then we have the absorption-desorption unit, and the vapor compression unit, which means that essentially we use the gas boiler as a heat source to drive the absorption cycle. So it's a heat pump that actually you use thermochemical energy storage to work. Then, of course, the gas-driven heat pump is also coupled to the compression cycle in order to provide the energy for cooling. And of course, we use the ground source, the heat exchanger, as the heat source or the sink, depending on the configuration of the system. So the idea was that using this kind of design, we were actually able to minimize the dimension of geothermal field, which was quite important considering that this was a historic building and we had a limited range of action in terms of stability of the system, in terms of drilling and so on. And this was done by using this kind of hybrid heat pump, because using this thermally driven heat pump requires lower amount of heat at the evaporator, which in return allows us to produce something smaller in terms of geothermal field. As I said, the final step was to actually integrate what we were designing within the existing system. So this is more or less the scheme of what we developed. So here we have the ground heat exchangers. Everything that is in the dashed purple line is actually the ADS unit with the chiller. So it's something which is within the hybrid heat pump that we developed together with Fahrenheit and the guys from CNR. And of course, we also had to introduce a gas boiler. Everything was connected to the existing piping. So it was connected to the domestic hot water, the floor heating, and the ventilation, the mechanical ventilation that was already serving the building. And then, as we will see later, we also try and interact everything that was in here with our building management system that was already there. This is more or less the technical room where we placed all of the elements that I was discussing. So it's a sort of storage room, to be honest, to begin with. And we placed inside there the storage tank and the two adsorption unit, desorption unit, and the chiller that were actually functioning in our pilot. Then, as I said, once you design and you make your calculation and you make your models, you need to somehow evaluate what you're doing. So we went through an extended monitoring campaign, both before the intervention, during the intervention, so the excavations and the works, and also after the intervention. In terms of pre-intervention monitoring, we focused on energy monitoring, microclimate monitoring, and structural monitoring. So we analyzed what was the actual electric, heat, and gas consumption of the building, what was more or less the microclimate condition within the building and outside the building, and what was the structural performance of our building in terms of comfort, structural damage, and ambient vibrations. Everything was done more or less considering the sensors that you see here in the slides. And these are some peaks of what we actually have within this building that I didn't tell you, but it's actually an office building at the moment run by the university. So that's why you see a desk here. It's actually an office building. It was a former stable, but now we have part of our offices and labs inside there. So after the designing and the monitoring, what we actually did, which was also quite an innovative part of this project, was to place everything within the HPIM model. So we produced a model that allowed us to have everything inside the model, everything that we designed and everything that we monitored in our buildings, both in terms of structural monitoring, but also human comfort monitoring. This is more or less the scheme of these HPMI. So as you see, we have the group of information that comes from the structural evaluation that is in blue, and the group that is actually coming from the comfort analysis of the subject within the building. So Our HPMI actually has some plugins within it that has inside all the information coming from the human-centric comfort monitoring in terms of vibration assessment that we're taking during the pre-intervention monitoring, which actually gave us good results. So the vibrations that we do have within the building are within the regulatory limits in Italy, so we can go through with our projects. And then, of course, we also have a plugin for the indoor microclimate. So our building tool allows us to have information and to charge information within the building, within the tool itself, in terms of indoor temperature, relative humidity, air velocity, and so on. And it also allows us to calculate the main comfort parameters like the PMV and the PPD. So we are able to know more or less what is the comfort condition for the building occupants in every time and in every part of the building itself. As I said, we also carried out additional structural performance like the vibration-induced damage assessment. This was very, very much important since, as I said, this is a historic existing building. So we had to be sure that our intervention, especially in terms of drilling, didn't damage what was already there. Also because it was also served by a very, very huge pre-generation system that actually served the whole village, to be honest, of Santa Apollinare, not just the building. So this was a very, very important part of the monitoring, and it allows us to have good results. So again, we are within the regulatory limits, and this is also a piece of information that is introduced within the HPMI. And finally, we also managed to place inside the same model information about the operational model analysis and the structural health monitoring. So we essentially know every now and then what is the condition in terms of response, structural response of our building, and we can use it to detect eventual damage in long-term monitoring in terms of SHM. So I've been discussing about everything that went through the design and modeling and implementation of this kind of pilot, but then of course we had to produce this, and this is more or less quick steps of the installation of the building. So we started the civil works in December 2020. We went through with the excavation, the structural health monitoring that I was discussing before, and also the radar and all the pre-intervention monitoring that also Tony was discussing and telling you about a few minutes ago. Then, of course, we went through with the excavation, which were 2.5 meters deep, as I was saying before. We used some sand to increase the conductivity and so have better heat transfer between the thermal fluid and the ground. And we used the sand both below and above the slinky heat exchangers, which were placed in place using a grid, a metal grid that allowed us to have more precise installation, as you see here. This is a pic of the kind of slinking heat exchangers that we were actually using. As you see, it's basic classic rings, tube rings, where actually the thermal fluids goes through. And also here you see the grid, and you see also the optic monitoring, the fiber optic monitoring that was installed by the Groen-Holland partner that also took care of the design of this slinky heat exchanger. This is another additional monitoring system that allows us to have some information about the thermal field in our excavation. We also introduced some drip water in order to increase the thermal conductivity of the ground, but we can actually go through this quite quickly. This is, of course, the backfilling of the field, and this is the main heat installation of the different components. So all the elements that actually produce our system physically, the heat pump, the boiler, tank, and chiller. This is the technical room with some of the partners that actually went through the commissioning, which is the next step. After you install everything, you go through the commissioning, and this took place in April 2021. Some other pics about our installation during the works, and the heat pump that you see on the top left of the slide, hybrid heat pump with the chiller. Final part, post-intervention monitoring. We more or less use the same kind of meters that we were seeing before, and we managed to have information about the energy consumption, microclimate, and structural monitoring in order to calculate more or less the efficiency of our system and have the COP of the system itself. Also, as a final step, we integrated all these information within our BMS that was already there, as I said, and we actually managed to have everything in control in every minute from the web page of the BMS, which is actually composed of two different elements. The control page, which is the one that you see here, so we can set air temperatures and relative humidity and so on within our building for every room, and we can check what happens in terms of all the parameters that you see here continuously. So to close, what went well with our project? We did manage to use energy retrofit by means of geothermal systems in historic building, which was very, very tricky, was a real difficult part for this application. Main tips for future application: if you plan to do something like this, if you want to try and do some retrofit in an existing historic building, be very, very careful with what are the existing constraints of the building. At least in Italy, we have huge constraints when it comes to art and the appearance of this kind of building. So you need to very well focus on these. We did manage, and this is also something that went well, to produce the building information model and place everything within it. So all the information from the comfort monitoring, from the geothermal monitoring, the structural monitoring, and so on. And this is something to take into into your mind when you plan to do something like this. Producing a BIM actually allows us and allows you to have some tool, which is a multi-purpose tool, a smart tool that has everything within it and can actually help you during the design stage, but also later on. Finally, we were also able to integrate all the new systems and controls in the existing BMS, which is also not so trivial, because as in our case, the BMS was already there. It was quite an old version, so it was quite difficult. So if you want and you plan to do something like this, be careful to integrate properly all the new components and the new monitoring in what is actually there in your system. What went wrong? We had to integrate several technologies and systems. So this was very, very much difficult. It took a lot of time to us. It was the GEOFIT actually involves a lot of partners. So it is all to be expected. If you plan to do something like this, make sure you have a complete planning of what you're doing in advance, and you right before, of course, before you start even the design, not only the installation. Another thing that went wrong, well, that took us a lot of time, was gathering all the permits from the municipality. So if you want to do something like this, test your ground. Always ask in advance for all the permissions and check the limitations, check the timings that you need to experience. And then finally, of course, we went through the operation and the installation during a pandemic. So you cannot really assume that there will be a pandemic. So it was quite difficult, also because we had lots of economic incentives in Italy for energy retrofit in the same period. So all the professionals were taken, and it was very, very much difficult to reach them. So in case you want to do something like this, of course, you cannot expect to have another pandemic, but please make sure you have a sort of backup plan, and you have at least 100 professionals that can help you with your design and your installation. And I am done. Thank you.